Right, so yesterday we looked at using the Pythagorean Theorem. Basically, if you're given a right triangle, you know two of the sides, we can use it to find the third side. Okay. Notice we haven't really done anything with solving for angles. Okay, Pythagorean Theorem only is used to find sides. If you want to find angles in a triangle, that's where trig comes in. That would be the next section if we were going to do a next section. Okay, sine, cosine, tangent. Some of you have already done that. If you don't get to it in geometry, you'll get to it when you take trig as a senior or pre-calc. Okay, so this is just a summary of what we did in 9.2. Okay, so this part you don't have to write down. So yesterday we learned that if a triangle is a right triangle, and this is what I think Luke had told us earlier, if you take the hypotenuse and square it, it's equal to the sum of each of the legs squared. Okay, that's the Pythagorean theorem. Well, the converse of that is also true. Okay, back when we studied logical statements in chapter 2, we learned that the converse isn't always true. But with the Pythagorean theorem, it is. Right, so this part is new. Okay, it's just the Pythagorean theorem switching the if and the then. So this says, if you square the length of the longest side of a triangle, and it's equal to the sum of the squares of the lengths of the other two sides, then the triangle is a right triangle. Right, so what we're doing here is we're proving whether or not I give you three sides, you tell me, do they form a right triangle? Versus last night, I gave you a right triangle, gave you two of the sides, and said find the third. Okay? In this case, I will give you all three, and you tell me, is it a right triangle? Yes or no? Okay, so this is the short way to write out the theorem. If c squared equals a squared plus b squared, then that proves you have a right triangle. Did anyone have any question on how this is different from what we did yesterday? It's similar, but it's the converse.
Isn't that like kind of implied in general when you do out the problem, like if it does equal b, and since you can only have Pythagorean theorem of the right triangle, like why would you even like need to explain that?
Well, what I'm going to do is give you a problem like this. I'm going to say, tell me true, false, yes or no, is this a right triangle? That's the kind of problem you'll have. So what you'll do is you'll plug everything into the Pythagorean theorem, and if it works, then you can say, yes, this is a right triangle. If it doesn't work, then you're going to write no.
Okay, Mr. Hager.
Did that make sense?
Makes perfect sense. You're amazing.
Thank you. All right, so let's just fill it in. Okay, first of all, we got to figure out what the longest side is. Some people get a little confused. They think, oh, right away, 113 must be the biggest. Well, remember, it's the square root. So let's just see if it really is bigger than 8 and 7. In this case, it will be. But it's always good to double check. Yep, so that is the longest side. All right, so let's fill it into the Pythagorean theorem. So this is going to be C, because it's the longest. Now, what about A and B? Which one should I let be A? Which one should be B? It doesn't matter. Exactly. Okay, they're the legs. You're just going to add them up. Okay, when you add, it's like saying you're going to add 5 plus 2 or 2 plus 5. If you switch them, it doesn't matter. It's the same thing. Okay, let's fill it into the Pythagorean theorem. And what I'm going to do is I'm not going to put equals. I'm going to put a question mark above it. Because we don't know this works. If it does, it's a right triangle. If it doesn't, it's not. Okay? So we'll just put a question mark. So does the square root of the longest side equal, the square of the longest side equal one leg squared plus the other leg squared? Okay. Marquise, what happens when you take a square root and square something? They cancel out. Okay, so all we're left with here is 113. Okay, 8 squared is 64. 7 squared is 49. Okay, let's just add up 64 and 49, see what you got. You get 113. So we get the same number on the left and on the right. What does that mean about this triangle? This is a right triangle. We just proved it. Yep. Okay, so determine if the triangle is below a right triangle. This one is yes. It might look like a right triangle, but remember we've learned through the course, you can't just look at a diagram and assume something. Okay, unless it's labeled, and this one wasn't labeled. Okay, even this one. Looks like a right angle. Okay, let's check and just make sure we find what the longest side is. It looks like it's probably 4 square root 95. Let's just make sure that's bigger than 36. There's the square root of 95 times 4. Yeah, a little bit bigger than 36. All right, so Alyssa, can you fill in my formula to check if this is a right triangle? Yep, 4, go ahead, I didn't hear you. Okay. Okay, just like that? You sure? Like that? And then squared. Good. So we're going to check if the longest side squared equals the sum of the two legs. Okay. For this, there's 2 ways you can do it. If you want to do it in your head, it's basically you square each number here separate. It's almost like the distributive property, except you're not multiplying, you're raising to a power. It's 4 squared times the square root of 95 squared. Well, 4 squared is 16. When you square root and square, they cancel, so it's 95. So it's 16 times 95. That's what you get on the left. Okay. Or you can type that whole thing into your calculator and just hit square. It's quicker for me to just type that in. Okay, it's 1,520. Okay, square 36 and 15. So there's 36 squared, 1296. 15 squared is 225. Add them up, we get 1521. Okay, so what does that mean here? No what? This is not a right triangle. It's close. It's very close. In fact, if we use trig, I bet this angle would come out to like 89.99 or something. It's very, very close. Or it could come out to 90.001. Maybe it's a little bigger than 90. Maybe it's a little smaller. I'll show you how to figure that out in the next part. Okay. But for now, let's just say that no, it's not a right triangle. We don't know if the angle is a little bigger or a little smaller than 90. But it's one of the two. Okay, and let's try our last one. Well, 2 more. Okay, how about Katrina? Can you set up my formula to check if that's a right triangle?
6 and then square root of 5.
Good, 6 square root of 5.
Equals 12 squared plus 6 squared. So then the parentheses around the 6 and square root of 5. So
Okay, well, all right, so when we do this out, 6 squared is 36. The square root of 5 squared is 5. We've got 36 times 5. Okay, 180. Okay, 12 squared, we should be able to do this. It's in our times tables. Kiera, what's 12 squared? 144. 6 squared is 36. And if you add 144 and 36, what do you get? Yep, you get 180, which means they are equal. This is a right triangle. Okay. Any questions on that? Anyone need to do a fourth one? You get the idea? Okay, so if they come out equal, right triangle. Don't come out equal, not a right triangle. Okay, so in those last two, sometimes it's hard to tell by the diagram, is the angle a little bigger than 90? Okay, like in that last problem, is it 89.99, a little smaller? Or is it like 90.01? Is it a little bigger? Okay, well, theorem 9.6 will tell us if the angle is bigger than 90 or smaller. Okay? And the reason we'd want to know that is because that's how we classify a triangle. If it's got an angle bigger than 90, we call it an obtuse triangle. If all the angles are smaller than 90, does anyone know what that's called?
An acute triangle.
An acute triangle. Okay, so it's two different kinds of triangles. Okay, so I'm going to write the theorem out in words, but then down below I put the equation, which I think is a lot shorter to copy. Okay, so theorem 9.6. The first part of it says, if you square the longest side of the longest side in the triangle, and it comes out less than the sum of the squares of the other two sides, then it's acute. So if you square the hypotenuse, and it comes out less than the sum of the squares of the other two sides, that's an acute triangle. So if c squared is less than a squared plus b squared, it's acute. And then theorem 9.7 is basically the same thing, except it's going to be for obtuse. Without me even showing you, anybody have a guess how this inequality is going to change when it's obtuse? Yeah?
C squared is bigger than a squared plus b squared.
Yeah. Yeah. So if you square the hypotenuse and it comes out bigger than the sum of the squares of the other two sides, that's when it's going to be obtuse. Okay, so I'll leave the writing up, but I really think I would just copy down this and this. Okay, so if you square the hypotenuse and it comes out greater than the sum of the squares of the two other sides, then it's obtuse. And if you write it that way, make sure you put c squared on the left, just like I did. It's kind of easy to remember. Greater than is bigger, obtuse. Less than is smaller angles, that's acute. Okay, if you write it differently, it might mess you up. So any question on theorem 9.6 or 9.7? All right, so let's see if we can use those theorems to figure out what kind of triangle we have here. Okay, now, notice the directions here. They first say decide if the set of numbers can even be a triangle. Well, what does that mean? Decide whether the side lengths here can actually represent a triangle.
So when you add them up,
Okay, what do you mean you add them up?
you have the two smaller ones and bigger than the bigger one. Is it how it works?
So you're on the right idea. You do add up two of the sides and then see if it's what?
Greater than
Bigger than that third side. Okay. If that doesn't happen, you don't even have a triangle. So if I gave you a problem like this and said decide whether or not these sides can form a triangle, if they do, say it's acute, obtuse, or right, this isn't even a triangle. 1 plus 1 is 2. 2 is not bigger than 10. You could not make a triangle with these sides. It would look something like this. There's 10, 1, 1. They wouldn't meet. Okay? So let's just check this quickly and see if we even have a triangle. 38 plus 77. Is that bigger than 86? Yeah. 77 plus 86, definitely bigger than 38. 38 plus 86, that's bigger than 77. So these sides do form a triangle. Okay? So we do have a triangle. So now I want you to tell me, is the triangle a right triangle, acute, or obtuse? Right, how about Ariel? Can you give me what my equation would be to check which one of those three it is.
38 squared plus 77 squared equals 86 squared.
Yeah. So I'm going to take the biggest side and square it, and that's equal to the sum. Well, you know what, actually? I won't even put the equals in between. I don't know if it's equal. I don't know if it's less than. I don't know if it's greater than. I'm about to find that out right now. So 38 squared plus 77 squared. Okay, so let's go through the arithmetic and see how these two sides compare. All right, 86 squared is 7,396. Okay, 38 squared is 1,444 plus 77 squared. That's 77 squared. Add them up. 7,373. What's the symbol that should go in here? Less than, equal, or greater than? That's greater than. So in this case, the hypotenuse is bigger. Let me make my sevens a little different so they stand out. The hypotenuse is bigger than the sum of the two legs. So what does that mean?
It's obtuse.
This is obtuse. Good. So when I write it, I'm always going to put the hypotenuse on the left, put the two legs on the right. That way it'll be set up just like this formula. Okay. Any question on that? Okay, and in this case, it's just barely obtuse. All right? It's not like this angle is going to be 150 degrees. It's going to probably be in the 90s, just a little bit bigger than 90, because this isn't really that much bigger than that. A little bit, but not like thousands and thousands bigger. Okay, next one. First thing, let's check if we even have a triangle. Denver, if you add 10 and a half and 36 and a half, is that bigger than 37 and a half? Yeah, definitely bigger. If you add 36 and a half, 37 and a half, that's bigger than 10 and a half. And if you add the first and the last, that's bigger than the middle. So these do make a triangle. Okay, Brian, what would be my thing that I would set up to figure out what kind of triangle I've got? What goes on the left?
Left would be 37.5 to the second.
Yep, to the second power. And what about on the right?
10.5 to the second.
Good, 10.5 to the second.
36.5.
Yeah. Okay, now just looking at it, kind of eyeballing it quickly, 36 and a half is almost as big as 37 and a half. So this number is going to be pretty big. And then you're going to add more to it. So my guess is the right-hand side is going to be bigger than the left. Okay? So I think we're going to need a less than this time. Okay, but let's check. 37.5 squared, 1406.25. Okay, take 10 and a half squared, that's just a little bigger than 100. 110.25 plus 36.5 squared. Okay, so you get 1,442 and a half. Okay, so my guess was right. This time the hypotenuse is smaller than the sum of the two legs. Okay, so this should be a less than. Okay, so how about Marquise? What kind of triangle is this? Yeah, acute. The hypotenuse squared came out smaller than the sum of the two legs squared. This is acute. Any questions how we figured out that this is acute? All right, and our last one. 818.24. Okay, well, if you check it real quick and you add everything up, it will work. 8 and 18 is 26. That's bigger than 24. 18 and 24 is bigger than 8. 8 and 24 is bigger than 18. Okay, so everything works there. All right, how about James? What's my thing I'm going to set up here?
24 squared,
Yep, we start with the biggest.
18 squared, 8 squared.
Okay, anybody have any thoughts on this one?
I think we're going to get an
Obtuse?
obtuse triangle.
All right, so 24 squared, we get 576. Okay, 18 squared, we get 324. 8 squared is 64. So we get 388. So in this case, definitely obtuse. Okay. Let me just double check, make sure I did 18 squared. Yeah, we did that right. Okay, so this came out quite a bit bigger, which means this is probably very clearly, if you were to sketch it to scale, obtuse. Okay. Any questions on that one? Oh, I skipped C. Well, C, I'm wondering if people can figure out, because we talked about this yesterday. Yeah?
It's a Pythagorean triple.
This is a Pythagorean triple. Okay, the two Pythagorean triples people usually remember are 3, 4, 5 and 5, 12, 13. Okay, 13 squared is 169. 12 squared is 144. 5 squared is 25. If you add 144 and 25, they will be equal. So this is a right triangle. Denver?
What's your favorite Pythagorean triple?
My favorite one? Probably 3, 4, 5. It's one of the two that I remember off the top of my head. And the numbers are in order, 3, 4, 5. Okay, you could also, kind of a harder question, something we wouldn't do in this class, but you could try to prove, are there more Pythagorean triples where all the numbers are right in order? Like 3, 4, 5. No numbers skipped, no integers skipped. Or could you prove it's impossible? That's the only one, and you could never have another one. Be a difficult question to prove, I think, at this level, but not too bad in like a number theory class. All right, so let's finish up with this one. Okay, so it says you're using strings and different stakes to mark the foundation of a house. Okay, and you want to make sure that the foundation is rectangular. Okay, so when you build it, you want to make sure the walls are perpendicular to each other. And after you stake it out, a friend measures the four sides to be 30 and 30 on one side, 72 and 72 on the other. And he says, okay, we're good. The foundation is square. It's a rectangle. Okay. Is he correct?
Not yet.
So if you measure all four sides of the foundation and come out like that, does that prove your foundation is a rectangle? No? What does this prove it is?
Parallelogram.
Yeah, all this proves is you have a parallelogram. All right, so let's just make a sketch of it. Here's your foundation. Okay, if this is 30, and this is 30. Okay, got opposite sides here that are congruent. 72, 72. If you have opposite sides congruent, all you've done is prove it's a parallelogram. I think this was in the homework. Okay, so is he correct? No?
Sir.
We have a parallelogram.
Right, no, sir.
Okay, so all we have is a parallelogram. Any question on why this is not a rectangle based on that information? Does anybody know what you could measure here that would actually be helpful? Measuring the sides, that's not really helpful.
Angles.
Okay, you could actually measure angles. Like if you had a transit, maybe you could shoot some angles and measure them. But the diagonal, right? If you really want to make sure that a doorway is square or a window is square, you measure the diagonals. Okay? Let's take a look at why. All right, so the other friend here measures the diagonals to be 78 feet. explain why this shows you that the foundation will be rectangular. So I'm not even telling you, will this determine if it's rectangular? I'm telling you it will. I want to know why. All right, so let's draw in our, does he measure both diagonals or just one?
Just one.
Okay, he just measured one. So if they're just going to measure one, then we've got to use the other information the other person had. If they measured both,
And they're the same.
and they're the same, then that would be different. But in this case, they're not measuring both diagonals, just one. Okay, so this is 78. What were they, 30 and 72? 30, 30, 72, 72. Okay, so what could I do here to see if this foundation is rectangular? Yeah, do the Pythagorean Theorem. Okay, let's do it on the top triangle. We're going to check and see if this angle comes out to 90. You're just going to use these three sides. It's just like the last couple problems I gave you. See if these form a right triangle. Right. So Jacob, what would be my formula to check if the three sides I circled form a right triangle?
And 30.
70, which one, 78?
72.
78 squared?
78 squared.
Yep. Oh, okay, I'm sorry, I set it up. No, I set it up the same way I did before. Yep, so 78 squared. And then what's going to go in these two?
30 in the first one. And 72.
72. Anything else on the right-hand side?
Squared.
Yep, each one of these is squared. Okay, so let's see what happens when we do it out. So we get 6,084. Okay, 30 squared, that's not too bad to do in your head, that's 900. 72 squared, 5,184. Okay, if you add 5,184 to 900, you'll get 6,084. Okay, so these do come out equal. So that proves that's a 90. But how does that prove that this is a rectangle? Because rectangle has to have all four angles 90. We only know this one.
Because it's congruent to the other triangle.
Right, these two triangles are congruent. Sides of 30, 72, 78. 30, 72, 78. They're congruent by side, side, side. Once we know triangles are congruent, then we can say corresponding parts are congruent. So that's a 90, that's a 90. All right? But what about these other two angles? How do we know those are 90s? We haven't measured them. They are going to be 90, but why? Well, there's actually a lot of ways you can discuss it. But remember, we already know this shape is a parallelogram, so it might be easy to use a fact about a parallelogram. Katrina?
Because like it adds up to 360, 90, 180, it has to be the same. So
Right. In a quadrilateral, all the angles add up to 360. You've already used up 180. And we have a parallelogram, so opposite angles have to be the same. You got 180 degrees left, and you got to split it equally between the two. 90, 90. Okay? So all four angles come out to 90. All right, so what we just went through, that's the reason why. Okay, any question on that? Now, a lot of times when people are measuring, like at a construction site or something, to figure out if it's perpendicular, you don't even need to measure all four sides. Really, you could just measure the diagonals. How come? If your two diagonals come out the same, why does that prove that this is a square door frame or whatever shape it's representing?
Because that means the corners are equally distant from each other.
That means the what?
The corners are equally distant from each other, so it makes it square.
Okay, it does mean the corners are equally distant, but unfortunately we don't have a theorem about corners being equally distant.
We should make one.
They should.
I'll make one.
Well, if you've cut your materials, right, and you know that you cut the bottom and the top the same, you know those are the same length because you cut them the same. So there's no question there. And if you cut, the frame that's going up the side of the door, you know you cut those materials the same. So you automatically know you have a parallelogram. Okay? So now that you know you have a parallelogram, there's all kinds of ways we could do this. We could prove that we have congruent triangles. Okay? We could measure the sides again, because if we've cut them, we know how long they are. And usually for a door frame, its standard is 36 inches, 3 feet wide. But all you got to do is measure these diagonals, and that'll prove that they are congruent. Okay? We're not going to go through a whole proof, but the idea would be based on congruent triangles. That's how you could show it. Okay. Any question on that? What I would probably do if you were going to do congruent triangles, I'd focus on this big one, and then show that one in red is congruent to this one in green. And then if you can show that they're congruent, you could say corresponding parts are congruent. So then both of these angles would have to be 90s. Using properties from parallelograms and congruent triangles. Okay? But I don't want to go through that whole proof right now. Okay? But that's the idea. Has anyone actually done that? Like in a trade, like if you're building something, measure the diagonals, make sure what you built is square, either door frame or foundation, anything like that. Well, I don't think we don't do foundations, but we build door frames.
Yeah, when you're putting in studs for like a wall, you have to measure if the studs are square, so you have to go with
You measure the diagonal.
yeah.
Yeah. If it comes out the same, you're good.
Yeah.
Yeah. There's other tools as well. Yep. All right. Good. Okay. So that's the converse of Pythagorean theorem. All right. So the homework, on that is on 546. Okay. 8 to 21 all. 26, 27, and 34.